Hello, everybody, and welcome to lecture, I think this is 17. 17 or 18, but I think it's 17. Hold on a minute. Sorry for the interruption. I think this is video 17. We've been talking about modulo arithmetic, congruences, and we are going to want to solve a number of congruences. Not only that, just like we solve equations, we solve congruences. And just like we solve systems of equations, we will solve systems of congruences also. So some of these things that we're going to learn today are going to be helpful immediately. Some of them, their value won't be readily apparent until we start doing systems of congruences. And then all of a sudden, they are going to be very, very helpful. Just like when we have equations, we have cancellation laws, which essentially say that we can divide both sides of an equation by the same non-zero number. We have cancellation laws in modulo arithmetic, which tell us under certain circumstances that we can divide both sides of a congruence by a certain number and still preserve the sense of the congruence. In about 15 or 20 minutes, I will make a more accurate comparison between dividing both sides of an equation by a non-zero number and dividing both sides of a congruence by a certain kind of number that I have not defined yet, but I will. Anyway, this is our first cancellation law. If CA is congruent to CB modulo n, and C and N are relatively prime, then we can cancel the C's. So do we get that? If the common factor C and N are relatively prime, we can cancel the C's from both sides of the congruence. And as an example, let's look at this congruence. Now we have a common factor on both sides. That's 10. So that's going to be our C. And 7 is going to be our N. And guess what? The greatest common divisor of C and N is the greatest common divisor of 10 and 7. And they are most certainly relatively prime. We can cancel. I don't have much space at the bottom, so let me do it over here. I have 10 times 3 congruent to 10 times 10 mod 7. And we just figured out that we could cancel the common factor from both sides. So we go zip, zip, and that leaves us with 3 being congruent to 10 mod 7. Now we could look at that and say, yeah, well, we could figure that out without canceling. We could take 30 take 100, and let's see, if we divide 30 by 7, we have 20. We have 4 times 7 is 28, remainder 2. And if we divide 100 by 7, we have 14 times 7 is 98, and a remainder 2. When we divide each side by 7, we have a remainder 2. Yep, they're congruent modulo n. So if we cancel, we're going to get something that's congruent modulo n. We could have done this without canceling. But can we always cancel? Apparently not, because if we can't always cancel a common factor from both sides of a congruence, then we wouldn't need a law like this, would we? So the key is, if the common factor and n are relatively prime, then we can cancel out that common factor. Okay, here's one where we can't really just take this number here and this number here and determine if it is a congruence, so forth and so on, because we really don't know what x is and we don't know what y is. Can we cancel the 10s from both sides of this congruence? What do you think? I'll tell you what I think. This is my C, and maybe just for the sake of memory aid, we'll say that this is C for common factor. That's just my thought right now, but hopefully it will work. C is the common factor. Here's N. And the greatest common divisor of C and N is the greatest common divisor of 10 and 7, which is 1. So we have the congruence 10x is congruent to 10y mod 7. And we've received the green light to cancel. And x is indeed congruent to y mod 7. Well, is it always going to be the case that we can only cancel if C and N are relatively prime? Maybe not. Just like if you take a revolver that has 6 chambers in it and it only has 2 bullets, and we put it to our head, we're not going to shoot ourselves in the head every time we pull the trigger. But when we pull the trigger, we're never going to know whether we're going to shoot ourselves or not. Same thing if C and N are not relatively prime. Occasionally, we may be able to cancel the C's and come up with the right answer, but more often than not, we won't. And if C and N are not relatively prime, there's really no way of telling when it's going to work and when it's not going to work. So the conventional wisdom is, if these things things are not relatively prime, we don't cancel because more often than not, what we get is going to be wrong. Let's look at some more stuff. Here's a nice example. 21x is congruent to 21y mod 3. Can we cancel? Greatest common divisor of C in N is the greatest common divisor of 21 and 3. And it's not equal to 1. But we can't cancel. We can't, or maybe I should say we shouldn't cancel. Just like I might tell my best friend, you can't drive intoxicated. But what I really mean is you shouldn't drive while you're intoxicated because he may choose to do it anyway. I certainly hope he doesn't. But yeah, we can cancel, but we shouldn't. Bad things are probably going to happen if we do. Let's take a look at a case. Let's see. Let's let x equal 5 and y equal 10. And let's see what happens. 21x is equal to, what, 105? 21y is equal to 210. Now, as it turns out, 105 is congruent to 210 mod 3. Uh, 21y, 21x. 105 is congruent to 210 mod 3. What happens if we cancel the 21s? If we cancel the 21s, we get that x is congruent to y mod 3. X is congruent to y mod 3. Is that true? Let's see. X is congruent. We divide by 3. X divided by 3 is 1 remainder 2. So x is congruent to 2 mod 5. Y is 10. If we divide 10 by 3, we get 3 remainder 1. So y is congruent to 1. Whoops. mod 3 here. Y is congruent to 1 mod 3. Now what's going on here? We canceled the 21s. We canceled the 21s. And by the way, without canceling, this congruence is true. We cancel the 21s and we get x is congruent to y mod 3, but is that really 2? Is that really true? X is congruent to 2 mod 3. Y is congruent to 1 mod 3. So no. This turns out to be a big fat false. And how did that happen? We canceled a common factor on both sides of a congruence, but the common factor was not relatively prime with n. Now, it could have worked for no other reason than just dumb luck, but it didn't, because this number, 21, and this number, 3, were not relatively prime. I'm going to depart from the direction that the book takes for just a little bit. For those of us who have had some abstract algebra, we may be familiar with this. We may also be somewhat familiar with this if we've had some finite math, or maybe I should say discrete math. That may be a better term. We're going to talk about zero divisors, or divisors of 0. And here's the definition of zero divisor mod n. Let a be a number between 1 and n, and notice that a is not equal to 1, and it's not equal to n. A is strictly greater than 1, strictly less than n. A is said to be a zero divisor mod n, or a divisor of 0 mod n, exactly when there exists another natural number b, with b between 1 and n, such that a times b is congruent to 0 mod n. And maybe now we can see why we call a to be a divisor of 0. We've been using the term divisor synonymously with factor. A is a divisor of 0 if there's some other integer that we can multiply a by to get 0. Okay. So a times some other integer is 0. A is a divisor of 0. We call it a divisor of 0 or a 0 divisor. Well, what about b? Does a get all the glory and a times b is 0, so a is a 0 divisor? Well, no. If a is a 0 divisor because a times b is 0, then b is also a 0 divisor. That's what this remark says. If we have a and b such that ab is congruent to 0 mod n, I beg your pardon. Okay, where were we? If a is a divisor of 0 by virtue of the fact that there's some integer b such that a times b is congruent to 0, shouldn't it also be true that b is a 0 divisor by virtue of the fact that there's some integer a congruent to 0? And that's what this remark says. this thing happens where A is between 1 and n, not inclusive, and B is between 1 and n, not inclusive, and A times B is congruent to 0, this remark says both A and B are said to be zero divisors mod n. And the next remark makes sense, as we can see zero divisors come in pairs. If A is a zero divisor, then there has to be some other zero divisor that we multiply it by to get 0. So if A times B is congruent to 0, A is a zero divisor and B is a zero divisor. Now this remark is kind of fitting. It says A is a zero, if A is a zero divisor mod n, the B that we multiply A by to get 0 mod n may be A itself. In other words, it may be the case that A times A is congruent to 0. And so the pair of zero divisors that gives us 0 is A and A. Let's look at some examples. Here's a good example. It draws attention to one of the remarks that we looked at before I erased the board. And I'll start off with a theorem first. The zero divisors mod n are exactly those numbers between 1 and n, not inclusive. The zero divisors are those integers a greater than 1 and less than n, such that the greatest common divisor of a and n is not equal to 1. In other words, they are those integers a that are not relatively prime with respect to n. Okay, let's look at an example. Let's have n equal 9. The zero divisors mod 9 are those integers between 1 and 9, not inclusive. Those integers greater than 1 and less than 9, such that a and 9 are not relatively prime. Okay? Those integers between 1 and 9 not inclusive, so that's 2, 3, 4, 5, 6, 7, 8. Okay? Those integers between 1 and 9 that are not relatively prime with respect to 9. Well, let's see. Are 2 and 9 relatively prime? They sure are. So 2 is not a zero divisor. Are 3 and 9 relatively prime? Hell no. 3 times 3 is equal to 9. So 3 is a zero divisor of 9. In fact, the pair of divisors that gives us 9 in this case is A equal 3 and B equal to 3. 3 times 3 is equal to 9, which is congruent to 0. Remember we said a little bit earlier that the B that we multiply A by to get 0 mod n may actually be A itself. This is one of those cases. Here's A, and here is B, which turns out to be A. Excuse me. Once again, I apologize. Where were we? 3 is not relatively prime with respect to 9, so it is a zero divisor. And it turns out to be its own complement as far as a zero divisor pair goes. 3 times 3 is 9, which is equal or congruent to 0 mod 9. What about this next person on the list, 4? 4 is relatively prime with respect to 9. So we can take 4 off the list. 5 is relatively prime with respect to 9. We can take 5 off the list. 6 is not relatively prime with respect to 9. They have a factor of 3 in common, so 6 can stay. 7 is relatively prime with respect to 9. As is 8. 8 is relatively prime with respect to 9. 6 is also a zero divisor. Well, what in the world would we multiply 6 by to get 0 mod 9? It has to be another zero divisor, doesn't it? In this case, 6 turns out to be its own complement as a zero divisor. Here's our A, that's 6. And here's our B, that's 6. 6 times 6 is 36, which is congruent to 0 mod 9, because 36 is 4 times 9. Now, is there anything else that we could do with these two zero divisors? They are their own complements as far as zero divisor pairs. 3 is its own complement as a zero divisor. 6 is its own complement as a zero divisor. Interestingly enough, in this case, they don't have to be their own divisor. And you probably see this already. Observe that 3 times 6 is congruent to 18, or equal to 18. And that's congruent to 0 mod 9. By the way, I didn't finish these off, and I suppose I should. 6 times 6 is 36, which is congruent to 0 mod 9. 3 times 3 is 9, which is congruent to 0 mod 9. Let's look at some more examples. Another example. Let n equal 12. The zero divisors mod 12 are exactly those integers a, with a between 1 and 12 not inclusive, such that a and 12 are not relatively prime. The zero divisors are not relatively prime with respect to n equal 12. So what are our candidates for zero divisors? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Are 2 and 12 relatively prime? Nope. Are 3, oh, wait a minute. We're looking for our zero divisors. So are 2 and 12 relatively prime? Yep. No. 2 and prime are not relatively prime. So 2 is a divisor, a zero divisor of 12. 3 and 12 are not relatively prime. So 3 is a divisor, a zero divisor of 12. 4 and 12 are not relatively prime. So 4 is a zero divisor of 12. 5 and 12, relatively prime. So 5 is not a zero divisor. 6 is not relatively prime with respect to 12, so it is a zero divisor. 7 and 12, relatively prime. 7 is not a zero divisor. 8, 12, relatively prime? Nope. So 8 is a zero divisor. 9 and 12, relatively prime? Nope. So 9 is a zero divisor mod 12. 10 and 12 relatively prime? Nope. So 10 is a zero divisor, mod 12. 11, relatively prime with respect to 12? Yes. 11 is not a zero divisor. Holy moly. Well, let's see. Since 2 is a zero divisor, mod 12, there has to be something that we can multiply 2 by to get 0 mod 12. And one of those things is 6. 2 times 6 is congruent to 0 mod 12. 3 is a zero divisor, mod 12. So there has to be something that we can multiply 3 by to get 0 mod 12. What do you think? And there are several answers here, just like there were several answers. Well, let's see. Now, I guess 6 was the only one up there. 3 and 4. 3 times 4 is congruent to 0 mod 12. Now, 4 was not the only candidate, was it? What was another one? 8. 3 times 8 is 24, which is 0 mod 12. Okay. Now, what about 4? Well, we have our answer right here, don't we? 4 times 3 is congruent to 0 mod 12. Was that the only possibility? I don't think so. What about 4 times 6? That's 24, which is 0 mod 12. What about 4 times 9? That's 36, which is 0 mod 12. Okay. And 6, holy moly. Well, we already saw that 2 times 6 is congruent to 0 mod 12. So 6 times 2, congruent to 0 mod 12. Is there anything else? Ooh, you better believe it. 6 times 4. 6 times 4 is 24, which is 0 mod 12. And 6 times 6. 6 times 6 is 36, which is 0 mod 12. Ooh. 6 times 8, yeah. 6 times 8 is 48, which is 0 mod 12. And 6 times 10 is congruent to 0 mod 12. Holy moly. And what about 8? Well, we saw that 3 times 8 is congruent to 0 mod 12. So 8 times 3 is congruent to 0 mod 12. And what about 8 times 6? Yep, 6 times 8 is congruent to 0. So 8 times 6 is congruent to 0 mod 12. And what about 8 times 9? What is that, 72? Which is 6 times 12, which is 0. Yep. So 8 times 9 is congruent to 0 mod 12. Wow, look at all of these zero divisor pairs we're coming up with, huh? Okay, 9. Well, where have I seen 9 before? 4 times 9 congruent to 0 mod 12, so 9 times 4. 36 congruent to 0 mod 12. I'm going to have to start up here, I think. 9 times 4 congruent to 0 mod 12. Have I seen 9 any other? Maybe I haven't seen 9 anywhere else. So 9 times 8, yeah. 9 times 8, and we said that was 72, which is 0 mod 12. Okay, and 10. Let's see. Have I seen 10 before? Oh yeah, right here. 6 times 10 is 0 mod 12. 10 times 6 is congruent to 0 mod 12. Now the point of all of this, in part, was to get us to see what all the zero divisors were, and their complements as zero divisors. There's another reason I was doing this as well. Be darned if I can think of it right now, but I'm sure it will come up and bite me in the rear end when I need it to solve a problem and I realize I haven't talked about it. Give me a moment to think. Now that my sanity's coming back to me, I think the other reason I did this was just to drive home the fact that the zero divisors, in this case mod 12, were all of those numbers between 1 and 12, not inclusive, that were not relatively prime with respect to 12. So if we have something between 1 and 12, and it is relatively prime with respect to 12, it is not a zero divisor. And this will be important. We want to know what our zero divisors are, and we also want to know what elements are not zero divisors. Because when we have a congruence, those are the ones that we can divide both sides by and still keep the sense of the congruence. Let me say that again. Those numbers that are not congruent mod n are those numbers that we can divide both sides of a congruence by and preserve the sense of the congruence. We won't introduce any false solutions. Okay, now what's the big deal with not being able to divide both sides of a congruence by a zero divisor mod n? Well, let's look at this. I'll make this a theorem. 3 is equal to 7. And here's my proof. 0 equals 0, right? The reflexive property of equations. Now I'm going to multiply one side by 3 and one side by 7. Well, I can do that because both sides are still equal to 0. So it is true that 0 times 3 is equal to 0 times 7. And now to get my result, I'm just going to cancel 0 from both sides. That's such a nice proof. I'm not sure that a little square box at the end is good enough. I think maybe I'll do the old Latin QED. Now, the impropriety of my approach here is obvious. Something that we cannot do with real numbers is divide by 0, which is exactly what I did when I canceled the zeros here. I divided both sides by 0. can't divide both sides of an equation by 0. If we could, that would really empower us to prove a lot of things that are absolutely false. We cannot divide by 0. We cannot divide both sides of an equation by 0. Back into the world of congruences. Analogously, we cannot divide both sides of a congruence by a 0 divisor mod n. Well, remember that theorem that we had earlier? If CA is congruent to CB mod n, and the greatest common divisor of C and n is 1, then we can cancel the C from both sides. Then we can divide both sides by C. Well, what was this theorem really saying? If greatest common divisor of C and n is 1, what was it really saying? It's saying if CA is congruent to CB mod n, and C is not a 0 divisor mod n, then we can divide both sides by C. That's what it's really saying. Let's look at this congruence. 15A is congruent to 15B mod 11. Well, I would sure like to cancel these guys. Can I do this? Can I do that? Did I just shoot myself in the foot or somewhere else? Is it legal to do that? Fifteen is not a 0 divisor mod 11. Or equivalently, 15 is relatively prime with respect to 11. So if 15A is congruent to 15B mod 11, A is indeed congruent to B mod 11. What about this one? 5A is congruent to 5B mod 25. Can I divide both sides by 5? Can I do this? Tell me the answer. We can't do it because 5 is a 0 divisor. Mod 25. 5 times 5 is 25, which is congruent to 0 mod 25. 5 times 5 is congruent to 0 mod 25. 5 is a 0 divisor. I cannot do this. And just for emphasis, I'll write it down again. No. Now here's a related question. Is it possible that A is congruent to B mod 25? It could be. possible. But it cannot be determined based solely on the congruence 5A is congruent to 5B mod 25. Algebraically, I cannot go from here to here because 5 is a zero divisor mod 25. Or to say it differently, greatest common divisor of 5 and 25 is not equal to 1. Those are equivalent. So I can't jump from here to here. Now, it may turn out that A is congruent to B mod 25, but we cannot make this, we cannot determine this based solely on this. Let's finish this up. A times B is congruent to 0 mod n. And greatest common divisor of A and n is equal to 1. Well, what's another way of saying that the greatest common divisor of A and n is equal to 1? Isn't that the same as saying A is not a zero divisor mod n? Well, we can divide both sides of a congruence by something that's not a zero divisor, right? And that's the first way that we'll look at this. A is not a zero divisor mod n. So this is what we can do. We're going to cancel this guy. We're going to divide both sides by A, which we're entitled to do because A is not a zero divisor mod n. We can divide both sides by something that is not a zero divisor. And we get B is congruent to 0 mod n. That's one way that we can reason on. Here's another way. We'll start right at the beginning again. AB is congruent to 0 mod n, and greatest common divisor of A and n equals 1. And that is to say, A is not a zero divisor. Mod n. So if B is not congruent to 0 mod n, then B would just be some number that we multiply A by to get 0 mod n, which would make both B and A divisors of 0. But see here, greatest common divisor of A and n is 1. A is relatively prime with respect to n, so A is not a zero divisor. If B were not 0, we'd have two non-zero numbers mod n, that we multiply by one another to get 0 mod n. And that would make both A and B 0 divisors. Remember, these 0 divisors come in pairs. One 0 divisor times another 0 divisor gives us zeros. They're both equally complicit in guilt. But we've already established that A is completely innocent. A is not a 0 divisor. The only way that if Z were a 0 divisor, the only way that we could multiply B by some non-zero number to get 0 is if A were another 0 divisor. The product of two 0 divisors will give us 0, but a non-zero divisor times a 0 divisor won't give us 0. A is not a 0 divisor. So no matter what B is, other than 0 itself, A times B is not going to give us 0. So here we can't reason, well, A times B is 0, A's a 0 divisor, B's a 0 divisor. Not going to work. If this is a case of two 0 divisors, or if this is a case of AB being congruent to 0, because B is a 0 divisor, A would have to be a 0 divisor also. They come in pairs. But we've established that A is not a 0 divisor. So a non-zero divisor times a non-zero divisor times a 0 divisor is not going to give us 0. The only thing that's going to give us 0 if this is not a 0 divisor is if this is congruent to 0. So we can't say on the basis of this, we multiply them together, we get 0, they're both 0 divisors. No. We've already established that A is not a 0 divisor. And if A is not a 0 divisor, the thing that we multiply it by to get 0, it won't be sufficient for this thing just to be a 0 divisor. It's going to have to be congruent to 0 itself. And I did a terrible job of explaining that. I'm sorry. But if this is going to be congruent to 0 by virtue of them both being 0, well, if this is going to be congruent to 0 by virtue of one of these being a 0 divisor, the other one's got to be a 0 divisor too. And we already established that A is not a 0 divisor. So how do we take something that's not a 0 divisor and multiply it by something and get 0? This other thing has to be congruent to 0. B being a 0 divisor isn't going to be enough. B is going to have to be congruent to 0. Let's analyze this. 4 times 30 is congruent to 0 mod 12. First of all, is it true? 4 times 30 is 120. And when we divide that by 12, we get a remainder of 0. Yep, 120 is equal to 12 times 10 with a remainder of 0. So this is true. Now, 4 is not congruent to 0 mod 12. 30 is not congruent to 0 mod 12. And technically, we can't say that 30 is a 0 divisor, because we say that 0 divisors of 12 are those numbers between 1 and 12, not inclusive, that are not relatively prime to 12. But let's see, what does 30 contain? 30 contains 0 divisors. And let me write this out nice and pretty. Contains as factors 0 divisors. And let's see. 2 is a 0 divisor of 12. 0 divisors of 12. What are they? 2, 3, 6. I guess that's it. 2, 3, and 6 are factors of 30, and they are all 0 divisors of 12. 4 is a 0 divisor. Of 12. So essentially, we do have the product of 0 divisors. We have 4, which is a 0 divisor of 12, times 30, which contains as factors 3 0 divisors of 12. So that's why we get 2 non-zero numbers multiplied together being congruent to 0 mod 12. Neither one's congruent to 0, but their product is. In the strictest sense, this isn't a 0 divisor, but it contains as factors 0 divisors, 2, 3, and 6. Okay, let's look at another one. Let's look at this one. 4 times 30 is 120. And let's see, that's 120 is 8 times 15. So 4 times 30 is 120, which is 8 times 15. 4 times 30 is congruent to 0 mod 15. And yet 4 and 15 are relatively prime. Greatest common divisor for 15 is 1. Or another way of saying this, 4 is not a 0 divisor of 15. Okay. Or a 0 divisor mod 15. So what gives here? Well, look at 30. 30 is equal to 2 times 15. And what about that 15 here? 15 is congruent to 0 mod 15. So why does this thing work if 4 is not a 0 divisor? Because 30 is congruent to 0 mod 15. 4 times 30 is congruent to 4 times 0 mod 15. And that's congruent to 0 mod 15. What do we make of this one? 6 and 25. Greatest common divisor of 6 and 25 is 1. Another way of saying 6 is not a 0 divisor. Mod 25. This thing is not a zero divisor mod 25. So whatever it's multiplied by to give us 0 has to be congruent to 0 mod 25. And another way we can look at this, B is congruent to 0 mod 25. 6 is not a zero divisor. So we can divide both sides. We can cancel the 6, and we get B is congruent to 0 mod 25. Okay, we're going to make this section real short. No theory. We'll leave the theory until a future lecture. We're going to talk about a few special divisibility theorems, and you may know one of these. Let capital N be any natural number, and let B be any natural number greater than 1. The place B place value notation for N is given by A sub M, B to the M, plus A sub M minus 1, B to the M minus 1, so forth and so on. A sub 2B squared, A sub 1B, plus A sub naught. Each of the A sub i's are greater than or equal to 0 and less than B. And notice here that we're talking about base B place value notation. In base 10, what do the coefficients range from? In base 10, don't we have numerals from 0 to 9? Similarly, in base B, we have natural numbers that range from 0 to B, but not including C. These coefficients can be 0 and anything less than B. In base 10, that would translate to the coefficients being anything from 0 to less than 10, 0 to 9. So let's look at a couple of, well, let's see, maybe I have a remark first. Okay. The base B place value notation for N is unique. There's only one way to do it. And here's an example. The representation capital N equals A sub M, B to the M, plus A sub M minus 1, B to the M, plus blah, 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 plus A sub 2B squared, plus A sub 1B, plus A sub naught, is more concisely expressed as A sub M minus 1, dot, 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 A sub 2, A sub 1, A sub 0. Notice that these are just the coefficients of the various powers of the base B. This is not multiplication here. This is just juxtaposition. They're just placed in a natural order from coefficient of the largest non-zero power of B in descending order to the coefficient of the smallest non-zero power of B. So this is the coefficient of b to the m. This is the coefficient of b to the m minus 1, and so on. Here's an example. In base 10, n equals 3 times 10 to the 4th plus 6 times 10 cubed plus 7 times 10 squared plus 4 times 10 plus 2 times 10 to the 0. This number is more concisely expressed as what? 3, 6, 7, 4, 2. And to be consistent with what we've been saying up here, if it's necessary, we put a 10 here so that we know we're talking about a base 10 number. And it's customary for us to put a comma here between thousands and hundreds. So the more concise way of expressing this place value notation for n in base 10 is to write it this way. The number n equal 246 base 10 is 2 times 10 squared plus 4 times 10 to the 1st plus 6 times 10 to the 0. This number, 246 base 10, can be represented in base 6 place value notation as 1050 base 6. So that's 1 6 cubed plus 0 6 squared plus 5 6 to the 1st plus 0 6 to the 0. Let me just convince myself that that's correct. Let's see. 6 cubed, I think, is 216 plus 0 times 36 plus 5 times 6 plus 0 times 1. 36, let's say, oops. That doesn't look right. Oh. 0 times 36 plus 5 times 6. Oh my goodness. Okay, thank goodness. Maybe it's time for me to quit. 246 base 10. That's equal to 1050 base 6. That's 1 times 6 cubed, 0 times 6 squared, 5 times 6 to the 1st, 0 times 6, 216 plus 30, 246 base 10. Here's our first theorem. We know probably a similar result for 3, but this is for 9. Let n be the base 10 place value representation. am 10 to the m, am minus 1, m to the 10 to the m minus 1, so forth and so on. Base 10 representation of n. Let S be the sum of the coefficients, a0, a1, a2, a sub m. Let S be the sum of the coefficients. Our theorem says that 9 divides n, the original number, if and only if 9 divides S, the sum of the digits. We won't prove this today, but we'll prove this in the next lecture. What we will do today is look at an example. Let's see, what do I want here? Let's call this something. Let's give it a name. like maybe Harold or Fred or maybe N. 16, 23, 27. 9 divides S. Therefore, 9 has to divide N also. And I think that's true. I don't think I'm a liar. Oops. Okay. So that works. In base 10 notation, 9 divides the original number if and only if 9 divides the sum of the digits. Let's look at another example really quick. Let's see. N equals 63, 42. Okay. S is the sum of the digits. 2 plus 4 is 6, plus 3 is 9, plus 6 is 15. Oops. 9 does not divide S. Therefore, 9 does not divide N. And if we do this out, I think we can verify this quickly. Okay, yep, 9 does not divide N. Now let me make a similar remark. The analogous statement holds true for 3 dividing N if and only if 3 divides S. And again, we'll remind ourselves that this is in base 10 notation. If we switch bases, we can throw all the rules out. Here's a result that's not nearly as well known. Let N be A sub M to the M, A sub M minus 1 to the M minus 1, blah, 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 blah. Be the base 10 place value expansion of the positive integer N. And now we define T to be the alternating sum and difference of the coefficients. A0 minus A1, A2 minus A3, dot, dot, dot. Negative 1 to the M minus 2, AM minus 2, so forth and so on. The significance of the negative 1s to the M minus 2 and so forth is just that the signs alternate. Positive, negative, positive, negative, positive, negative, till we reach the end. And when we add all these things up, we get t. 11 divides the natural number n if and only if 11 divides t. Let's try that. Let's look at an example. Let's take n equal 29, 172, and t, let's see, we start with the ones digit, subtract the next, add the next, subtract the next, add the next, and what do we get? We get 2 plus 1 plus 2 is 5, minus 7 is negative 2, minus 9 is negative 11. Clearly, 11 divides t. 11 times negative 1 is t. Therefore, 11 also divides 29172. Let's look at another example, our last example, our last anything. Okay, let n equal 910. T we get by taking the digits and adding and subtracting in reverse. So 0 minus 1 plus 9 gives us 8. And notice this, 11 does not divide t. Therefore, 11 does not divide n equal 910.